let's consider the following example. You're going to be buying some costumes for a costume party that you're hosting and you're going to be providing for. And you go to the store and you ask how much the costumes cost, and they have a bulk discount if you buy enough of them. So, this is how things typically go. Let's say that costumes cost $20 each, but if you buy 10 or more, the cost is only $15 each. Well, this is a good deal if you want to buy 10 or more costumes. We would like to, in many cases like this, set up a function that tells us how much it's going to cost us to buy a certain number of costumes. So, we want to build a function, capital C of x, where C is the cost to buy X costumes. Now, there are a few things that we could try based on this example, but the two most natural things for us to try both fail, and sort of for the same reason. So we could try the following. Well, we're told at the beginning that the cost to buy costumes is $20 each. And so if I want to buy, say, 5 costumes, I calculate my cost by taking the price times the number of costumes. So we could try the following. We could try saying that the cost of buying X costumes is 20 times X. And so this would tell us that the cost of buying 5 costumes is 100, which works. The cost of buying 1 costume is just 20. But it fails when we try plugging in something like the cost to buy 10 costumes. This function would tell us that the cost to buy 10 costumes is 200, because that's 20 times 10. But in fact, we know that's not the case. We know that if you buy 10 or more costumes, they only cost $15 each. So in fact, the cost to buy 10 costumes should only be $150. And this doesn't work. So that means that this formula that we got, C of x equals 20x, doesn't always work. It works okay with plugging in 5 costumes or 1 costume, but it doesn't work if you try plugging in 10 costumes. Well, we could try going with the other number we've got. We could try saying, well, what if we try using the function C of x equals 15x? That'll work with the third example that we've got. If we plug 10 into this function, we do get 150 out, which is what we want to get out of this. But we don't get the right answer when we try plugging in 1 or 5. If we plug 1 into this function, we would just get 15. And that would tell us that the cost to buy 1 costume is $15, which we also know isn't true. So the problem here is that we can't use a single formula to represent this function, and that's because the function changes behavior. The cost to buy these costumes changes, and so we need to use different formulas depending on what quantity of costumes we want to buy. This is precisely where piecewise defined functions come in. They're going to give us a way to represent situations like this. So we're going to use piecewise defined functions. And let's build the piecewise defined function for the problem that we just did that will explain what's going on. And with a piecewise defined function, the function will involve two different formulas, but those two formulas will apply at different times. So we would say that the cost to buy X costumes is equal to 20X if X is less than 10. Because the formula of each costume costing $20 only applies when the number of costumes we're buying is less than 10. And the cost being 15X applies only if X is greater than or equal to 10. This is the anatomy of a piecewise defined function. You will have two or sometimes more formulas. And for each one of those formulas, you'll be told a certain portion of the domain of the function where that formula applies. So this tells us where our formula applies. So when I go to evaluate something like C of 7 here, what I do to get this is I first find the interval on the right side of the function description containing our input. So in this case, if we want to find C of 7, what we do is we look at our two intervals on the right. X is less than 10 and X is greater than or equal to 10, and see which applies. Do we apply the first formula or the second? So we see here that 7 is less than 10, which means that we are going to use the first formula, because the first formula applies whenever our input is less than 10. So we're going to use the first formula. And so we get that C of 7 is equal to 20 times 7, because we're going to use the formula now, the first formula, because our input satisfies the condition for us to use the first formula. So C of 7 is equal to 20 times 7, which equals 140. So the cost to buy 7 costumes is 140. On the other hand, if I take C of 20, what I do is I look at the input here, and I ask the input of 20, and I ask which of the conditions on the right-hand side of the function description does this input satisfy? Is 20 less than 10, or is 20 greater than or equal to 10? Well, 20 is greater than or equal to 10, and therefore, that means that I'm going to use the second formula for this input here. And so that tells us that C of 20 is equal to 15 times 20, because we use the second formula here, which gives us 300. So that tells us that the cost to buy 20 costumes is 300. So let's look at a couple more examples of these piecewise defined functions and evaluating them, and then we'll look at how we can graph them. Okay, so let's let f of x be given by x squared minus 1 if x is less than or equal to 2, and 3x if x is greater than 2. So this is another typical example of a piecewise defined function. And let's evaluate f at 0, f at 5, and f at 2. So then let's go ahead and do that. If we want f of 0, then the first thing we need to do before plugging in anything is figure out which of the formulas we're going to apply. And so we look at the conditions on the right. We say, is x less than or equal to 2, or is x greater than 2? Well, in this case, x, our input, is 0, and 0 is less than or equal to 2. That means that we're going to use the first formula, and so we'll get 0 squared minus 1, which gives us negative 1. So in this function, when the input is 0, the output is negative 1. And so when we go to graph it, that means that the point 0, negative 1 will be on the graph, but we'll leave that for a moment. F of 5, we do the same sort of thing. We look at our input 5 and say, which of the conditions does 5 satisfy? Is 5 less than or equal to 2, or is 5 greater than 2? Well, 5 is greater than 2. That means that we're going to use the second formula, 3x, and replace x with the 5 that is our input. So we get 15 out of that. And then finally, f of 2. Here's where, of course, you do have to be careful that you make sure to use the right formula. For f of 2, is 2 less than or equal to 2, or is 2 greater than 2? Now, only one of these things is true, and so make sure that you're very, very careful about which one you choose. In this case, 2 is less than or equal to 2, so we're going to use the first formula. 2 is not greater than 2, so we can't use the second formula. So f of 2 is 2 squared minus 1, which gives us 4 minus 1, which is 3. So that means that the function has an output of 3 when the input is 2. So this last bit illustrates an absolutely vital piece of defining piecewise defined functions here. The intervals of definition, these intervals over here, which define when we use each of the formulas in the problem, they cannot overlap. Now, full disclosure, there are occasional situations where it might be okay for them to overlap because you happen to get the same number out of both formulas when you plug in the overlapping number, but even there, it's not necessary. So your best practice when working with piecewise defined functions is to make sure that your intervals of definition never overlap. Make sure that for any input falls into at most one of the intervals in your function. It can fall into none of them because the function might have a domain that's restricted. Its domain might not be all real numbers, but you can never have a single number fall into more than one of these intervals of definition. Otherwise, you don't have a function anymore because you got more than one output for the same input. All right, one more example. Actually, sorry, no, we want to first go to graphing these functions. All right, so let's talk about graphing piecewise defined functions. Now, various people have various ways that they like to do this. Mine is the following. Here's my preferred strategy. What I will do is I will graph each formula in the definition, then erase the parts I don't need. The reason why I do this is a lot of times the parts that you don't need, that you're not going to include in the function, are the parts that are most useful for graphing it, like y-intercepts and things like this. So what I like to do is graph each formula in the definition, erase the parts I don't need. Now the parts I don't need are the parts that don't lie over that formula's interval of definition. Let's take an example. Let's take our first example from the problem. Let's take c of x is equal to 20x if x is less than 10, and then 15x if x is greater than or equal to 10. Now, in this particular problem, negative values of the variable x and negative costs don't make sense. They just aren't relevant in the problem. So I will graph x's along the bottom and my cost along the top, and let's see, how ought we to do this? Let's see, I want we'll make 300 up here. We'll make each of these marks 20. So 20, 40, 60, 80, 100, 20, 40, 60, 80, 200. And then along the bottom, we'll use a slightly different scale here. We'll go ahead and use each mark as 2. So that's 4, 8. Oh, I'm sorry. Each mark is 1. That's what I meant. 12, 14, 16, 18, and 20. So let's use this right here. So what I will do to graph this function, first I'll go ahead and graph y equals 20x. And for the first stage, I will go ahead and ignore the restrictions over here of x less than 10. I'll ignore those. I'm just going to try and graph out the function y equals 20x. And so I see that the graph of y equals 20x has a y-intercept of 0, because we could write this as y equals 20x plus 0, and a slope of 20. So if I start here at the point 0, 0, that's the y-intercept, and then to get to the next point, I will go over by 1 and up by 20. That'll give me a slope of 20, over by 1, up by 20, over by 1, up by 20, and I'll get this line right here. Now let me try to do that efficiently. There we go. All right, so there's the graph of y equals 20x. And if that's all that the function was, then we'd stop there. However, now we look at the restrictions. We see that this is only supposed to apply when x is less than 10. So what we want to do now is we want to find the point on the graph that corresponds to an x value of 10. And that's right up here. We have the point 10, 200 on the graph. And so now we know that the blue line that we've got is only supposed to apply for x values less than 10. So this is only going to apply when we are looking at points to the left of 10 on the x-axis. So that means that we're going to eliminate all of the parts of the graph that lie to the right of that. Now, furthermore, we want to replace this point here with either an open circle or a closed circle, depending on whether that function, um, or whether the function actually takes the value 10 comma 200 or not. And we can read that from the fact that this is a less than symbol. So the less than symbol means that the point on the graph of y equals 20x isn't included, because the blue line only applies when the values of x are strictly less than 10 but not actually equal to 10. So the graph of the function will come right up to 200, right up to the point 10 comma 200, but won't actually reach it, because the blue line doesn't apply when x actually equals 10. All right, so there we go. Let's do the second one. All right, so now we've got the line y equals 15x. And once again, that's y equals 15x plus 0. So we can take the point 0, 0 on this graph. Now here, this has a slope of 15, which means that I can find a point on the graph by moving to the right by a certain number of, by a certain value of x, and then moving up by 15 times that. So in this case, I'm going to start at 0, 0, and instead of going over 1 and up 15, because I don't have 15 marked very nicely on my graph, I'm actually going to go over 4 and then up to 60. And I'm going to do that because 60 is actually one of the marks that I have on my grid, because my vertical marks are going up by 15 each. So this point right here is the point 4 comma 60, and it's on the green graph. So let's go ahead and graph that line. And again, let me try and get this nicely. All right, so there's our green function if we ignored the interval where it applies. So now let's apply that interval. We see that this is only going to apply when x is greater than or equal to 10. So once again, we want to know where on the graph, where on the green graph has a y-coordinate of 10. And we see that if we take 10 and plug it into the green function, 15x, we get 150. So that's going to be the point right there. And we're going to eliminate everything to the left of that, because the green line only applies when x is greater than or equal to 10, not less than 10. And so now we look here and see, because this formula applies when x is greater than or equal to 10, we're actually going to get a solid point. Since the point 10, 150 is included in the full graph of f. 150 is actually the output of this function when you plug 10 in, and so we get a solid point here rather than an open point that we got for the blue. So this can get pretty messy, but once you have this, you can then just erase all the parts that you don't need, or perhaps go to another um, graph now that you know what the shape is and redraw it. We're just going to go ahead and erase here. And erase all the parts of the blue line that don't apply over to the right, and then all the parts of the green line that don't apply. We don't have the 0.460 on there anymore. That was just to help graph the function. And so we're left with this function composed of the blue line and the green line. And so this is a typical way that you would graph a function like c of x. You'll notice that this graph is sort of broken there at 10. We say that this graph is not continuous at 10 because there's a break in the graph there. That is often the case with piecewise defined functions. You often have these jumps in it. Those are okay, and those often have an interpretation based on the problem. So remember that in the context of this problem, the y values or the c values are the cost to purchase x costumes. So the 200, the 0.10 comma 200 is how much it would cost to purchase 10 costumes if you didn't have any sort of discount, if you just purchased all of them at that full $20 price. Whereas the 0.10 comma 150 tells you that the actual price of buying 10 costumes, given that there is the discount. That jump there, that vertical jump of 50 represents the $50 that you save by using the discount when purchasing 10 costumes instantly as you switch over from one cost regime to another. All right, let's do one more example of this. Let's do the next example, or the other example that we had. We had f of x is equal to x squared minus 1 if x is less than or equal to 2, and we had 3x if x is greater than 2. So let's go ahead and graph this out. Now, sometimes when doing this, you'll have graphs that you will need to use some of your previous knowledge about. For instance, on this one, we might have to refer back to transformations of functions. So we'll go ahead and do 1, 2. We'll have each of our tick marks represent 1. So our first graph is x squared minus 1. And so we know that the original graph of x squared is a parabola which goes through the origin and a few points here. But x squared minus 1, remember, is going to shift that graph downwards. And so we can take each of the points that we know are on the graph of x squared and shift them down by 1 to get points on the graph of x squared minus 1. So let's do that. We know the point 0, 0 is on the graph of x squared, so the point 0, comma, negative 1 is on the graph of x squared minus 1. We know the points 1, 1 and negative 1, 1 are on the graph of x squared, so the points 1, comma, 0 and negative 1, comma, 0 are on the graph of x squared minus 1. The points 2, comma, 4 and negative 2, comma, 4 are on the graph of x squared, and so the points 2, comma, 3 and negative 2, comma, 3 are on the graph of x squared minus 1. Thus, putting these together, we can try and smoothly draw a graph of y equals x squared minus 1. So there's the first function, but we know that this only applies when x is less than or equal to 2. So that means that we can erase every part of this graph that occurs to the right of 2, because this graph only applies when x is less than or equal to 2. That means when we're looking at x values that lie at 2 or to the left of 2 on the x-axis. So that means that we can erase all of these points, and then we can put a nice solid point here at the point 2, 3. We know it's solid because of the less than or equal to that is in the definition here. All right, so next we can graph the other part of the function. We've got 3x, which applies when x is greater than 2. So if we start off by just trying to graph 3x, we see that, again, this is a linear function, and it's got a y-intercept at 0 and a slope of 3, so it's going to go through the point 1, 3, and then through the point 2, 6. I'm going all the way up to 2, 6 because I know that an x value of 2 is going to be important to me in a second. And so, graphing it out, we get a graph like this. Now again, we are only interested in the portion of this graph where the x values are greater than 2. So we're only interested in portions of the graph that are to the right of the point 2 on the x-axis. So we're going to erase everything on the graph that was to the left of 2. And then we look at the point that we've got here and decide, is this an open circle or a closed circle? Well, of course, it has to be an open circle because this is a greater than 2 condition here in the interval of definition. So this is the basic idea behind piecewise defined functions and graphing them. It really is just a matter of graphing the individual formulas involved and then just erasing the parts that you don't need. You'll notice that this graph here does pass the vertical line test. If you draw a vertical line anywhere on this graph, it'll only pass through the function once. The only place where that's not totally obvious, is at the point 2. But there, you'll notice that it passes through an open circle and a closed circle, and that's fine because the open circle actually isn't a point on the graph. It just indicates that the points come up close to that, but never actually reach it. So that's how we reconcile that. All right, the other topic that I want to look at right now is the floor function, or the least integer, the greatest integer less than or equal to function. I usually just refer to it as the floor function. So let's look at the floor function, and this function has a lot of applications in many things, especially involving computer science and other things like that. So this is a new function. It's got a notation that looks a little bit like absolute value, but it behaves differently. For any real number x, the floor of x is, we've got two notations that we'll use. The notation that you'll see most often in mathematics is this, where you've got sort of two square brackets, but without their top bars. So vertical bars with a little lower lip on either side. But you'll also see in the book, uh, the authors use this notation, sort of a square bracket with double bars on either side. And it's defined to be the greatest integer that's less than or equal to x. So, for example, let's look at a few examples of this. So, if I look at the floor of 2.3, that's going to be the largest integer that is less than or equal to 3. So I know that 2 is less than or equal to 2.3, but 3 isn't. And so this is going to be 2. I will look at the floor of 5. Now the floor of 5 is just 5. The floor applied to an integer just gives that back itself because 5 is in fact the greatest integer that's less than or equal to 5. The floor of pi is equal to 3 because pi is approximately 3.14, etc., 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 and the greatest integer less than or equal to that is 3. The floor of 3/4, floor of the fraction 3/4 is 0. That's the greatest integer less than or equal to x. And the place where we do have to be a little bit careful is when working with negative numbers. So what's the floor of negative 3.6? So for this, remember that we can use the number line to keep track of where things are in terms of what's greater and what's less. So let's say we've got -1, -2, -3, -4. Now negative 3.6 is about there. So if we want the greatest integer that's less than or equal to -3.6, what we do is we take that point and we move to the left on the number line until we reach an integer. In this case, that integer is -4. And so the floor of -3.6 is actually -4. Now the reason why I point that out is that it's a common mistake to think that what the floor function does is it just ignores the fractional part of the number, but that's not true. That's not true. The floor function moves down to moves left on the number line until it gets to an integer. And when we're working with negative numbers, that means that the floor of -3.6 is -4. The floor of -7.1 would be -8, and so forth and so on. So this is the floor function. One of the things it's most useful for is when working with problems that that involve quantities that sort of jump up in discrete amounts. So let's look at an example. So let's suppose that you produce apple cider. Now, each barrel contains 10 gallons of cider and sells for $55. If you produce X gallons of cider, how much money will you make? Now, the reason a question like this will involve the floor function is because in this problem, you can't sell cider that you haven't barreled. The only way that you sell your cider is by barreling it and selling those barrels, which means that if you have cider left over that can't fill up a whole barrel, then that's going to go to waste. You're not going to be selling half barrels or anything like that. You're only going to be selling full barrels. And so we want to find an expression that tells us how much money we're going to make. And so the first thing we want to see is, well, how many barrels are we going to produce? So we can look at the following. So each barrel contains 10 gallons. So X gallons fills X over 10 barrels. But of course, this doesn't really make sense if X isn't a multiple of 10. If X is 15, we wouldn't say that we fill 1.5 barrels. And if X is 19, we wouldn't say that we're filling 1.9 barrels or anything like that. In fact, the number of barrels that we fill is going to be the floor of X over 10, because it's going to be the greatest integer we can get that that is less than X over 10, less than or equal to X over 10. Fills X barrels, and we should say maybe with some left over. For example, if we produce 35 gallons, that means that we'll fill 35 over 10, or rather the floor of 35 over 10, which is the floor of 3.5, which is 3 barrels. And therefore, if we're filling the floor of X over 10 barrels, that tells us that we will make 55 times the floor of X over $10. Because $55 is how much each barrel sells for, and if we're producing the floor of X over 10 barrels, we will make 55 times the floor of X over $10. This is a type of situation that we might want to use the floor function in. Now let's look at the graph of the floor function. So let's graph things out. And this is one where it's going to be less useful to plot out specific points than to reason it out in our minds. So let's talk about what happens if X is between 0 and 1. If X is between 0 and 1, greater than or equal to 0 but less than 1, then that means that the floor of X will equal 0, because that means that 0 will be the greatest integer that's still less than or equal to X. So that means that the floor function will look like this for the interval from 0 to 1. So if x is between 0 and 1, then the floor of x is 0. Now, if x is equal to 1, then the floor of x will be, the floor of 1 is 1, so we definitely get the point 1, 1 on the graph. But then we can say that if x is between 1 and 2, but not equal to 2, then the floor of x is equal to 1. We can use the same sort of idea here. So if x is between 1 and 2, then the floor of x is 1. And similarly, if x is between 2 and 3, then the floor of x is 2. If x is between 3 and 4, then the floor of x is 3, and so forth and so on. And so we get this sort of stair-step pattern that goes up the graph and gives us this. So this is what the graph of the floor function looks like. You'll notice that it has a lot of jumps in it. We could try describing this as a piecewise defined function, but in fact it would have to have infinitely many intervals of definition. So it's really better off that we just have a function by itself to do it. Now, a similar related function is the ceiling function. So we can look at the ceiling function, where the ceiling of x is the least integer that's greater than or equal to x. The graph of the ceiling function looks sort of similar to the graph of the floor function, but slightly different. So notice that if x is between 0 and 1, but not including 0, then that means that the ceiling of x is equal to 1, because that's the smallest integer that's greater than or equal to x. So that means that we actually get a graph that looks like this, with a solid dot over here on the right. And then we get another one right here, because if x is greater than 1, but less than or equal to 2, then the ceiling of x is equal to 2. And we get a similar pattern going up. So the ceiling function carries many of the same kinds of behavior as the floor function, but we use it in slightly different ways. Here's an example of an application problem where we might use the ceiling function where the floor function doesn't do what we want. So let's say that a mechanic will charge you $200 for parts plus $50 per hour or portion of an hour that he works. What is his charge if he works X hours? So here we have two components to the charge. The $200 for parts, that one's just going to be added on at the end. We're not going to worry too much about that. But now we want to think about well, how many hours is he going to work, and how does that play into his $50 per hour or portion of an hour. And this is where the ceiling function comes in. Because if he works 7.5 hours, then that means that he's going to charge $50 times 8 because he worked for 7 hours and then a portion of an hour. So he's basically just rounding up by rounding up to the next nearest hour. If he works for 2.1 hours, he's going to charge 50 times 3. So he's going to charge you for 3 hours there. But of course, if he works for exactly 2 hours, he's going to charge 50 times 2 because then he just works the 2 hours. So that means that his hourly charge is going to be 50 times the ceiling of x. The ceiling could also be thought of as the round up function, and the floor is the round down function if you remember how things work when you're dealing with negative numbers. So the hourly charge for this mechanic is going to be 50 times the ceiling of x. If x is some number that's not an integer, we're going to go up to the next highest integer and multiply by that. So that means that the total cost for this mechanic is going to be 200 plus 50 times the ceiling of x. So the ceiling function and the floor function are very useful in contexts where you're dealing with quantities or variables that could conceivably be fractional, but you only want to consider either the next integer greater than it or the next integer less than it. So that's what the floor and ceiling functions do for us.